Cheering.
It's working.
Time, come inside.
It's working? Okay.
Yeah. So once I have the mic, then I have the sound. Okay, welcome back. Post lunch session, we have 3 talks, and so I think everybody is around, right?
Yeah, some more people are coming.
Okay.
Okay, we can, up to you.
So first talk is by Anoop, and he's going to talk about bridging the gap between experiments and simulations of glasses using machine learning technique, right? Yes.
Thank you.
And at 30 minutes, I will raise my hand.
Perfect.
And, okay.
Like the last speaker, I will acknowledge your raising hand. So, thanks a lot for this invitation, and it's really my pleasure to be here giving a talk on what we've been doing in the space of glasses for last couple of years. So before I get started, I just wanted to give you a broader picture of what we do in our lab. I'm not a glass physics person per se, not yet. Who knows, right? So I was not a glass science person. I became a glass science person. So why not move towards something more exciting? So what we do in our group is that we try to have an end-to-end framework for materials discovery, and primarily in the field of glasses. Silicate, oxides, chalcogenides, etc., etc. So if you think of this problem, what we have been trying to address is, now it's very popular. You have this idea called co-scientist, but essentially that's what we are trying to build for a glass research, right? So first, what you need is information extraction. You need to know what is out there in the literature. You need to have information from tables, text, images, etc., synthesize them across these modalities, and then try to be able to get a good guess of whether what your theory is, whether what your composition is, etc. So to this end, we have built several tools. By the way, if you're interested, you can check this out. MathScibert was one of the first material science language model in the world. Now we have built this LaMAT, which is large language model for materials trained on around 6 million papers. So that's the first materials domain large language model to the best of my knowledge. And once you have this, the second part of this is in silico analysis, which is simulating them and trying to understand. So simulating could involve basically using atomistic simulations or continuum simulations, and we work at both scales, because when you're thinking of a device, you need to really think of multiple scales, as one of the previous speaker was also invoking, right? So we try to address this problem by AI-driven interatomic potentials using AI for generative modeling. For example, generating disordered structures or generating trajectories, etc. And then finally, once you're convinced of this aspect, then you go towards self-driving labs, which is automated experiment. And here is one of our recent work where we showed that an atomic force microscope could be completely automated with a simple English language instruction. So you can just give it command as, just perform the experiment and give me the root mean square roughness and the friction of the surface. It does this entire thing by itself and then gives you the answer. Sorry? Coffee? Yeah, this is actually very easy. In fact, in one of these machine learning conferences, I do have the video, I can show it to you. They have this robotic arm which automatically makes coffee. It's much slower than humans, by the way, so the queue is much longer, but it can still make a good coffee, It can still make a coffee. So the idea is basically democratizing research in some sense and making it accessible to people, and also accelerating the scientific discovery in the fields, right? So, and just to give you an example, in this particular work, we took 100 experiments and benchmarked all 100 experiments by giving simple English language commands, to get a sense. But I will not be talking about this today. I will be talking about glasses, and how did I get into glasses? I got into glasses through radiation damage. I'm a civil engineer by training, and during my postdoc, we were funded by a project which asked, what is the mineral that I should be using in concrete when I'm putting concrete in nuclear power plants? He said, okay, let's simulate and then try, because I knew molecular simulation at that point of time, and I was looking for problems that could be solved with molecular dynamic simulations, and this seemed like a nice problem. So we started working on irradiation of silica, and we then extended it to a large number of minerals, silicate minerals, and we kind of realized that glass can be a good surrogate. I mean, I think this is a very simple statement. That's not the exact conclusion, but the energy landscape dictates the radiation-induced disordering was the conclusion. And with this, we could give a recipe of what minerals should be chosen when you're using it in nuclear power plants. Great. So today what I'm going to talk about is primarily on glass modeling. And for those who managed to read the abstract, which I believe is nobody, this is very different from what I have written in the abstract. So if you're interested in what I wrote in the abstract, please talk to me. I can have a separate discussion with you. But there are some overlap of people here who already listened to a part of my talk, and then I thought that I should make it more interesting and do justice to those people as well. So I'm not going to talk about energy landscape, which is what I was supposed to talk about as per the abstract. But what I'm going to talk about is atomistic simulations, and inherently there is a problem when you're doing atomistic simulations of glasses. All simulations are wrong. Why are all simulations wrong? Because the real glasses are made with a cooling rate of something like 1 degree Celsius or 1 Kelvin per second or something to the tune of that, whereas atomistic simulations have a cooling rate of 1 Kelvin per picosecond. So there is a difference of 12 orders of magnitude in atomistic simulations and experiment. This is okay if the system was equilibrium. Unfortunately, glass is not. So there is a huge gap between experiments and simulation, and what you try to do is somehow have compensating errors that address this gap. But here we are trying to look at some of these challenges. For instance, how to capture phenomena at long time scales, capture complex interactions at short and medium range length scales, and learning directly from experiments. In other words, what we are trying to ask is, to make a simulation meaningful, can we align it as much as possible with experiments and learn directly from experimental data instead of saying that this is the limitation of simulation and I will be doing it this way, right? So that's essentially what we are going to do. And for this, the primer is differentiable simulation, okay? So I'm just going to give a brief introduction of what differentiable simulation is. So the idea of differentiable simulation is, okay, just give me 1 second. This is supposed to animate. It did not. So let me do it right away. Now it is animating. Okay, so the idea is, let's take a simple example of C equal to an output which is y minus tan hx into wx plus b. It's a simple function, right? Now when you compute this function, what you have is a computational graph. So you, for example, go from this particular x, okay, forward, do w times x, and then take this output w1 and add it to w2, and then keep going along this computational graph. In differentiable simulation, what you do is that while you are creating this forward graph, you instantaneously compute the gradient of that function and save it as a symbolic function, okay? So for example, when I do w1, I also do dou w1 by dou w, which would give me x. So I would save wx as the function and the gradient as x at this point. At this point, I would do dou w2 by dou w1, which will give me simply 1. So I would save this variable w2 and its gradient, w3 and its gradient, w4 and its gradient. So finally, when I want to do dou c by, let's say, dou w, what I will do is I'll just take the product of all these functions that I have already computed, which is dou c by dou w4 into dou w4 by dou w3 into dou w3 by dou w2 into dou w2 by dou w1 into dou w1 by dou w. And because of chain rule, I will get the derivative. And the advantage is now I have converted the gradient operation to a multiplication operation, okay? So this is essentially the idea. How do you do it in real atomistic simulations? So here is one simple example. I know it's a bit clumsy, but let's try to just quickly go through it. So let's say I start with positions and velocities. I go first to Ri minus Rij, which is Ri minus Rj. This is my distance. And then I apply Leonard-Jones function, for which I will use the sigma here, right? And then get the potential. I'll get the gradient of the potential, which is my force. From there, I'll get the acceleration. From the acceleration, I will use some symplectic integrators like velocity Berthier or whatever, and then I get my updated position and velocity. So when I want to take the gradient now, I will calculate whatever the output is. Maybe I calculate the radial distribution function using the positions. So now what I would do is I take the gradient of the radial distribution function and go all the way backwards. Okay, that means dou of that whatever loss function is, let's say gradient of actual radial distribution function minus predicted radial distribution function with respect to the previous one, which would be dou r, and then I keep going backwards, and dou r by dou v, dou a, and dou v by dou a, and all of these gradients backwards until I get to this particular one, and I update my potential parameters, for instance. That means now my Lennard-Jones potential parameter will be updated as sigma plus, the gradient of sigma times some, length scale parameter. So just like your gradient descent, now you can go backwards and update potential parameters directly through the simulation, and this is the idea of differentiable simulation. Yes, you can do multiple steps. Accordingly, your computational graph will become larger and larger, which is what I am going to talk about. So you can do 100 steps, whatever, and then go backwards through all the 100 steps. You can do that also, but then that will be an input, right? Because delta t is an input for your simulation. You can do on the fly also. There is nothing that stops you from doing it, because at any point what you need to do is the computational graph creation, right? As long as your simulation is meaningful, because if you take large delta t, then it's no longer meaningful. But as long as your simulation is meaningful, you are fine. So the advantage is that you can take output of a simulation directly with respect to any input parameters. So it could be gradient with respect to position, it could be gradient with respect to force field parameters, or it could be even gradient with respect to temperature, because in MD simulation temperature is also an input that you give, right? So that's the interesting part of differentiable simulation. It's a fairly emerging field, but it's a very interesting field. So why is it interesting? Because there was this work in 2020 where this group of people, which is Cranmer and couple of people, developed this idea of Lagrangian and Hamiltonian neural networks. Okay, so the idea of Lagrangian neural network is very simple. Let's say you have a double pendulum. Okay, it's a very complex equation that you have, and typically you think of a machine learning model. What you try to do is that you give the input, which is current state, and then try to predict the new state. Okay, for example, this is a simple regression problem. They said this is a bad idea, because when you do this, you are not conserving energy, you are not conserving momentum, you are not respecting any equations of motion. So they said that instead of doing this, feed the position and momenta to a neural network and let it predict the Lagrangian of it. Okay, but you don't know what the Lagrangian is, right? So you won't be able to directly train. But what you do is take the Lagrangian and put it into the Euler-Lagrange equations of motion and get the acceleration and get the new position. Once you get the new position, you can say your error is predicted new position minus actual new position, and when you train it, they show that in that effort and exercise, you end up learning the Lagrangian of the system. Okay, so without having access to the Lagrangian, now you learn the Lagrangian and Hamiltonian of the system. This was the idea that they said. But we started looking at it more closely, and we felt that this particular problem or method is only suited if you have very simple degrees of freedom, because you see you have only q and q dot. If you have more degrees of freedom, let's say I have 100 atoms, then all of this will go to a neural network, which does not make sense, because we know that atomic systems are permutation invariant, in the sense that it doesn't matter which atom I pick first, it should have the same energy, right? Whereas neural network is not permutation invariant. The order in which I give the atom positions matter in neural network. I cannot just change it randomly, for example, right? So what we try to do is something interesting, and it's what is going to be the first thing that I'm going to talk about. For this audience, I'm not going to explain molecular dynamics simulation, but this is just one iteration of molecular dynamics simulation, which is what we are going to use to ask this question: can we learn the interactions directly from the trajectory of atomic systems? Quick intro to one more point, which is graph neural networks. So we try to, instead of using a neural network, we try to use something called a graph neural network. The idea is very simple. You represent atoms as nodes and bonds as edges. So now you have a graph, and from each graph you are familiar with your neighborhood. You do something called message passing. So you get information from your neighbors, and from there you predict the energy of each atom, and then you sum up, you get the total energy, then you use the usual stuff that you do in MD simulation and get the updated positions and velocity and continue. So this is the idea of a graph neural network force field, or when you're using graph neural network to predict the energy and forces. The interesting part here, as I'm going to talk about, is for example, when you use LJ, you know the functional form, you know the potential parameters. But when you use graph neural network, is it truly interpretable? And when you have this particular system, how do you train this to have a meaningful, energy and force is what I am going to talk about. So this was one of our first work where we try to take inspiration from this work from Cranmer and then try to put a graph neural network and called it Hamiltonian graph neural network. What it does is very simple. It represents a molecular system as a graph, and once you have the graph, then you basically take information from your neighbors, and finally you predict both its energy and pairwise energy. Okay, so this comes out of each bonds will predict the pairwise energy, and each node will predict its own energy, and then you sum up, get the total energy, and once you have kinetic energy and potential energy, you get the Hamiltonian. Once you have the Hamiltonian, you basically apply this Hamiltonian equations of motion and then get the next position and velocity. Okay, so in the initial time when we do this, it has not learned the Hamiltonian, so you would get very bad numbers. But what you do is that you try to minimize the error between the predicted position and actual position of one loop of MD. It could be multiple loops of MD also, but you try to minimize the error between this, and then while minimizing the error, it learns the weights in such a fashion that it actually gives you the potential and kinetic energy of the system without having access to this, and you learn the true Hamiltonian of the system, or you learn the approximate Hamiltonian of the system as close as possible to the true Hamiltonian simply by learning on the dynamics. Okay, and just to recall, this is the Lagrangian equation of motion, Hamiltonian. So the only point that I want to tell you is that once your graph neural network predicts this quantity which is Lagrangian, you don't need anything else, right? You don't need to know the mass, or you don't need anything else. Just the Lagrangian will allow you to give you the entire dynamics. So I mean, the reason why I wrote 3 is we wrote 3 variants and ended up writing 3 different papers. So one on Hamiltonian, one on Lagrangian, and one on graph neural ODE. But each of this had a slightly different theme as well. Okay, so how did we test this system? We started with very simple systems because it was to begin with an idea that we wanted to make sure works. So we took a very simple 5-link spring system, and then a 75 particle Leonard-Jones system, a gravitational system, and then real silica. Okay, so real silica, which is a density function, ab initio MD simulations of silica at high temperatures. So this is what you have. So 4 different systems with very different characteristics, but all systems follow Hamiltonian dynamics. That's the underlying theme, right? So then we did generate the trajectory of each of this, and then 100 trajectory, each having 100 steps is using as the training data, and then we try to see if it is actually learning the dynamics or not. Now here is the interesting output. So the way you read it is that the first one corresponds to a pendulum system, the second one corresponds to a spring system, third one the first one corresponds to spring system. Yes, first 2 corresponds to spring system, this one corresponds to a Leonard-Jones system, and this corresponds to a pendulum system. That's why you have kind of a, it's a double pendulum, so it's still a chaotic system. The interesting part we see is that without training it on kinetic energy or potential energy or forces, you see that the predicted kinetic energy and predicted potential energy is exactly the same, in the sense that it is learning the kinetic energy, it is learning the potential energy, and it's learning the forces pretty accurately. Okay, one can argue this is a very simple system. Yes, indeed, but yes. Here is kinetic, here is potential. So we are learning it separately and then just adding it as a Hamiltonian. But it's a neural network, so you can always see each of these are pieces. So I can just take each of this piece and then see what is the output that it's giving, because it's taking some input and giving output at each layer, right? So I can always look at what is that. I understand that it is kinetic energy. If you don't understand what it is giving you, then you just cannot compare it with a ground truth. That's it. You just take the whole Hamiltonian, and it still works. Right. So this was quite interesting for us, that it's respecting the phase space. I mean, that's not really a surprise because you are using Hamiltonian dynamics, so it should respect the basic things of Hamiltonian dynamics. But the interesting part was that without training on energy or force, you can learn the energy or force, was a very interesting aspect that we really found. And then we tried to see, once it is learned, does it generalize? So it of course does generalize. We trained it on like 5 particle system, generalizes to 5,000 particles, because you are learning at a graph level. So now you can generalize it to any size, right? And we realized that this is a good technique because now you can take experimental data, right? Because experimental data is purely trajectory and our learning also relies only on trajectory. I would still have to make some assumptions on the dynamics, whether it is Hamiltonian, Lagrangian, or is there some dissipation, etc., or is it Brownian. And I would also have to make some assumption whether it is pairwise interaction, three-body, etc. But once I do some basic stuff, I can learn the interaction directly from trajectory, and this was what got us excited. But more interestingly, what we did is, as I said earlier, each of these are neural networks. So you can really visualize what is learned by the neural network. And here we saw that the potential energy is learned as mgh, kinetic energy is learned as half mv squared. For a harmonic potential, we really learned the harmonic part when you just visualize the pairwise part. But most interestingly, even for a Lennard-Jones system, we see that, so this red dotted line is the actual one, and the blue lines are the predicted ones, okay, from our system. So we see that for a Lennard-Jones system, binary Lennard-Jones, it learns this separate interaction separately without us training it on any of this. Yeah, I mean, of course, we give the feature that these are two types of particles and there are two types. But other than that, we are not doing anything else. Yes? Yes. I mean, see, this machine learning model will learn on what the loss function is. So now, if you try to fool it by saying this is a Hamiltonian, try to learn the Hamiltonian, it will learn an effective Hamiltonian that may or may not capture the dynamics of your simulation, right? And this is something, another thread of work which we are excited about, that for example, we can use this for automated coarse graining. I can give the beads and I can make myself the beads and then give the trajectory of beads. Now I can learn what is the effective Hamiltonian of this trajectory of beads, assuming it follows a Hamiltonian dynamics, and there are more subtleties to it because when you coarse grain, things can get messy. Yeah. Right. So what I'll tell you what we did and what we can do. So what we did was we decoupled its own interaction, which is given by V, and pairwise interaction, which is given by Vij. Okay, and we said that this approximates every other interactions. Okay, for example, in silica you have multi-body interactions, we know, but we just said this is the effective, like a BKS potential, let's say, this is your effective potential. But if you're really interested, you can have hypergraphs. So you can have 3-body, 4-body terms and then effectively learn it, but it becomes too complicated at that point of time for us to make the training stable and also to even interpret. We have not tried it, but in principle, it can be done. Right. So just for the fun of it, what we did after that is, once you have this blue dots, we tried to use symbolic regression and then try to retrieve an equation out of it. For example, once you have an equation, then we can do the simulation whatever we want. We don't even have to rely on this graph neural network. And here is the result. So this is the original equation. For kinetic energy, harmonic spring, we actually get almost recover the exact equation. And for binary LJ, it's quite interesting. For 0, 0 and 1, 1, we recover 12, 6 and almost the same parameters. But for 0, 1, we really don't recover the exact equation. It's a 9, 6 potential that is learned. And yeah, probably because we don't have this part represented properly. So if you have more data, probably this will learn better. But yeah, this is what we have. But I think already this is very interesting that you can have now an equation out of your neural network and then use this equation for your further simulations. Right?
What is 0, 0, 1, 1?
No, these are just particles, A, B, B, A, B. Yeah, so just it's the Python nomenclature of 0, 0, 1, 1 and 0, 1. Yeah. We did it for silica also, and we trained it on trajectories, and it was quite interesting that we are able to learn pair distribution function OSI, SI, SI, OO very nicely. And even the structure factor, which is somehow corresponding to the long range correlate. See, it's not trained on any of this. That's important to remember. It's trained only on trajectories, right? And it's able to simulate this even medium range interactions correctly of even SI, 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 which is basically this angle. SI, SI, SI is this angle, and we are able to learn those also reasonably correctly by simply training on it. So this got us excited. We started to move towards more real systems. Silica is one example. But we tried to move towards more interesting properties also. Instead of learning just trajectory, can we use now differentiable simulations to optimize elastic modulus? can we use it to optimize, other interesting properties? And this is what we did. So we took silicon, it's a classical system, and there are two potentials for silicon that's there in the literature. People have studied it to beaten it to death. Shrikant also has done a lot of work on this in different angles. So Stillinger-Weber and EDIP are the two potentials that we took. And here is the DFT value of elastic modulus of it, the tensors. So if you look at the potentials, the interesting thing that you see is that it almost always reproduces the C11 reasonably well. Original one, C11 is given because this is like that's what you worry about typically when you use uniaxial compression, etc. But it gives you the other values very bad, which is C12 and C44. So what we wanted was, we used differentiable simulation, and the idea was to basically run the elastic modulus calculation, get the elastic modulus. Your loss function would be predicted elastic modulus minus actual elastic modulus, and back propagate it to optimize epsilon and lambda, which is the potential parameters, so that your entire matrix of elastic modulus error is minimized. And when you do this, the interesting point that I want to show you is, we are able to optimize the force field in like 6 iterations. Okay, just in 6 iterations it converges to the global minima. I mean, this is a convex problem, so we have a global minima because it's just elastic modulus predicted and actual. And irrespective of where you start, you always go to the minima. So potential training, which took things like, it was one PhD thesis, developing one interatomic potential for one system, used to be at least one PhD thesis in glassy systems, etc. So now you can do this in like 6 iterations, 7 iterations, and just get the elastic modulus for your system and tune it for any property of interest, and which is what I'm going to show. So elastic modulus is one just example, but you can do it for phonon density of states. For example, here you see Stillinger-Weber, this is the actual one, and then when you really optimize it, you can see it comes much closer, and then you have this optimized parameters for Stillinger-Weber that gives you minimize the error between predicted and actual vibrational density of states. And you can do this for multi-objective also. For example, include elastic modulus and phonon density of states, and then have this potential parameter that reproduces these properties correctly. Mind you, it will reproduce that property correctly, but that does not give you any guarantee on any other properties. Okay, I mean, this is very important to remember, that when you optimize the interatomic potential for one thing, you can expect it to work, at best for that thing, and at worst not even for that thing. Right? So this is what happens when you optimize an interatomic potential. Anything that you get beyond that is bonus. Yeah, exactly. So this is depending on whether those are competing or complementary, right? So in this particular case, this is what we see, and that's why I kind of show this comparison with elastic modulus only and combined one. So you would see that when you do this elastic modulus only, the elastic modulus is better fitted, whereas when you do the combined, elastic modulus is not so well fitted, but then you get the phonon density also fitted well, right? But the broader point is, we have a tool to do it now. That's the main point to drive home. Right. So once we started, yes. You have, oh, okay, thank you. Right, so once we did this, see, I did pay attention. So once we did this, we tried to ask, can we extend it to Brownian dynamics? And this happened to be the next paper which we wrote on BrogNet. Here everything remains the same, but the equations of motion now changes because it's Brownian equations of motion. So you will use this Euler-Maruyama integrator, and you will have those Brownian dynamics, etc. But again, learn the dynamics directly from trajectory. So still we did the same thing, that here the loss function slightly changed, because once it's Brownian dynamics, it does not make sense to say the loss function between predicted position and actual position. What we do is we match the distribution now. So your loss function would either be like a Jensen-Shannon divergence, or KL divergence, or those, or it could be something like negative log likelihood loss. So different loss functions could be used, but the idea is that you match it. So here you can see the circle is the actual one and the square is the predicted ones, and we can see that it actually gives a reasonable agreement. And again, we did the same thing that we did earlier, which was to see what is the learned interaction, and it was quite good. And it also could be scaled to any number of atoms. So you learn it from 5 particles, Now you can do, this is I think 5,000, yeah, 5,000 particles, and you can learn the Brownian dynamics, simulate the Brownian dynamics of 4,000 particles. Once we did this, we tried to see, can we take it experimental data and then learn the effective interaction from experimental data. So, you know, we are not an experimental group, so I've not had a lot of success in getting trajectories of experimental data. So at that point of time, Walter Kobe, who is a good friend and well-wisher, suggested that I reach out to Eric Weeks, and he has a lot of experimental data on colloidal systems, which is what I did. So this is a very nice data that Eric gave of a trajectory of, so here you can see the number of particles as the time progresses, and here, you know, it kind of is like a deposition. So it's like a 2D system, it's depositing and then gets saturated. So we try to take all this, you know, radial distribution functions and then try to learn the effective interactions of this from the radial distribution functions. And when we did this, what we did was that we assumed a functional form, okay? We tried 3 functional forms. We said we can take Morse, we can take LJ, we can take WCA. We could have done it with a graph neural network also, but we just thought this is more interpretable and meaningful to do. So again, you do the prediction and get the trajectory and then get this, you know, try to minimize the error with respect to this trajectory. And when you do this, here are the potentials that are learned. So you start from here and then you kind of settle here. This is for Leonard Jones, you start and settle here, and this is for WCA, you start from here and then settle here, okay? Now, how do you test whether any of these potentials that you got is meaningful? What we did is we took a quantity that was not shown for training, which is, you know, average phi6 versus volume fraction. This was obtained experimentally. So we took all those volume fractions and then tried to see what is the physics that is learned and what is the physics that was obtained experimentally. And we saw that with very few data of just 4 pair distribution functions, we were able to reproduce the phase, you know, the phi6, which is the orientational order for all the volume fractions very, very, very nicely. So that means now with very sparse data, you can actually learn. And here is some additional interesting example that we did. We tried to see from a single RDF can we learn. And I don't know if you can see, but the minima is somewhere here. So when you learn from single particle as a single pair distribution function, this is Morse, LJ and WC and the parameter space. So this is like the loss landscape of these systems. So you see that you don't converge to the minima when you learn only from 1 RDF, but when you start training it from 4 RDFs, then we see that it converges to the global minima, which is somewhere here for this particular system, you know, all these 3 potentials. Okay, great. So this is an idea of predicting force field, but there is a second part of it about which I might not be able to talk about. Do I have like 2 minutes to talk about it? Okay, great. So the second thing that we thought we can do, and this is very, very interesting. If I'm not able to talk about it today, I will talk about it tomorrow surely, because I have an overview talk and I will bring this as part of overview. What we try to do is, can we use this to predict properties? You know, we were optimizing force field, that's good. But can we use it to predict properties that are derivatives? And we took a very challenging problem, which is viscosity. Can we predict viscosity, not predict, compute viscosity directly by automatic differentiation? It's not prediction. We are doing automatic differentiation and actually getting the viscosity. So for this, we use the slowed equations of motion, and viscosity is computed as d sigma by d gamma dot. So since gamma dot is an input for your equations of motion, you can now do automatic differentiation and get the viscosity from it, just the way you do, you know, training force fields, etc. So when we tried this, what happened is that we saw that it just explodes, okay? After a few steps, the gradient starts exploding. And we were not able to get any meaningful value of viscosity until only this earlier region, you know, it kind of saturates here. But after that, the gradients really explode, and then, you know, you don't get anything meaningful. So we tried to investigate where is this explosion of the gradient coming from, okay? I mean, these are just multiple measurements that suggested that this is converging. I will not talk about it. But the gradient explosion is coming from trajectory derivative. And I think this is an important point which needs to be understood. And we try to kind of suppress this trajectory derivative using some Lyapunov exponents that was computed as the dynamics of it. And what we were able to do is that when you actually scale it with this Lyapunov exponent, we are able to get the viscosity predicted correctly and stably. So here is the viscosity value. When you just scale this viscosity with this Lyapunov exponent, you are actually getting the viscosity value. And this is not just for one system. We tried it for WCA, LJ system at multiple temperatures, multiple density, and we are able to, you know, get all of this viscosity correctly predicted. of course at high temperatures only, okay, because if you have very low temperatures, the viscosity will be like too high, so it becomes difficult. But this is from just 100 steps. So from 100 steps of simulation, now you can get equilibrium quantities which otherwise require Green-Kubo kind of things, which is like, you know, large trajectories. With this, I conclude. I think differentiable simulation is truly a future of the simulation, and we can use that to learn interaction laws, computing properties, geometry optimization, and dynamics of differentiable simulation require really further investigation, and I think this would be a very interesting area for us to understand how trajectory gradients explode and how the dynamics of this, and I think this is the right community to think of these problems and come up with meaningful solutions. And I just want to point out one of our recent commentary that we wrote, which is real AI advances require collaboration. This is because I see that the same, just echoing what Giulio said, we see that the same ideas that are existing in glasses and statistical physics is relearned by AI community, and many ideas in AI community is not even percolating to the statistical mechanics and physics community. So I think once we have this meaningful collaboration, I think that will lead to more interesting research and for better understanding. The work would not be complete without thanking all the funding agencies, but most importantly, all the undergraduate and doctoral researchers of our group and my collaborators, and these are specifically the people who contributed to this work. Suresh Bishnoi's PhD thesis, and Ryan is the one who did the viscosity work. And of course, I've been discussing a lot about this with Shrikant and my collaborator, Sai and Ranu, and the complete list of collaborators with whom I've been working, and all the graduate students in our group who has contributed very meaningfully to this work is here. So I'm just the marketing manager of the group. The real work is done by those people. Thank you.
Thank you. So we can have a couple of quick questions. Yes, Giulio.
Can you treat also stochastic equation with memory?
Yes, I think so. So in fact, this Brownian dynamics story is a story that we just recently explored, and the student graduated. So there was nobody to explore it further. But I think that's just the starting of it. I think a lot of systems that follow certain dynamics, stochastic dynamics, could be really explored, and we might be able to even like understand many, like for example, effective potentials and things like that from this, maybe even in memory systems. So I do not really thought about this problem, but I'll be happy to chat. But I don't see anything stopping us from exploring that.
Okay, first then you, then
So
Monica,
what happens when the data that you input has inaccuracies in it?
You will learn an inaccurate potential.
So I'm referring specifically to the colloid trajectories. The particles have errors in their coordinates.
Right.
So, I mean, what does that lead to?
This is the reason why we did not train on trajectories in the colloidal system. We trained it on the radial distribution function, which is an averaged quantity.
Well, that's
So-
also from the coordinates.
Sorry?
The radial distribution function is
Yeah,
also
it's
from the
from
coordinates.
but the expectation is that the peaks that you capture are meaningful.
Well,
and
they
the
are
overall
effectively
distribution.
convolved with the error that's introduced by the coordinates. So the coordinates are loosely speaking Gaussian distributed. With the coordinates you measure are loosely speaking Gaussian distributed compared to what they really are, with the result being that the peaks in the G of R are effectively a convolution between
Right.
some Gaussian and what it really is. So I'm asking, what is the consequence of that for your inferred pair potential?
Right. So let's try to decouple this into two scenarios. One is when I have minor errors, for example, one particle missing, two particle missings, etc., or things like that. I think that would be averaged out when you calculate.
That
the
has no
RDF.
impact.
Huh?
That when you miss a particle, it has no impact on the measurement. It's the error in the measurement of the coordinate that impacts the G of R.
Yeah. So how would you address this?
I don't know. I'm not trying to address it.
I mean, I think this is the situation with any experimental data, right? I mean, you can question whether this experimental data has error. So how do you infer anything meaningful out of this?
I'd say it would depend on the accuracy of the quantity you can measure.
Okay.
So these particular errors actually become quite significant when the colloids are dense. But it can take other properties, like, I don't know, something like temperature, one can measure to 1 part in 10 to the 6, so that it's not very relevant. I mean, but
No, this is, yeah, you're absolutely right. So basically, what you're saying is that the confidence of measurement should be taken into account while training, and we should ideally train it on quantities that we are more confident of, right? Yeah, I completely agree to this. I'm not an experimentalist, so I would go by what an experimentalist suggests is to be the best method. But I also understand and take the point that can we be more systematic about this and include this error somehow in learning? Is that what you're trying to ask?
I don't know, I'm just observing that that's
Yeah,
a
yeah,
limitation.
yeah.
Yeah, one
I mean,
can
I think
include
we
errors.
can talk about it, but I think we can be more principled about this. I agree.
We will discuss it later,
Yeah.
and then Sarika, then you pass the mic. That's how.
Anyway, he has got your attention and he can tell.
It's not on. I don't think it's on.
Okay, thank you for inspiring talk. So in computer physics, computational chemistry, people started to work on surrogation of molecular dynamics simulation. So the idea is to speed up solving Newton dynamics. The bottleneck of molecular simulation is that you need a really small time step. So their idea is to make a very large time step, sort of making a surrogation model for molecular dynamics simulation. So in your community, did you discuss this kind of application?
I don't know which community you are referring to, but yes, we have done some work on this specifically. We have trained I will be talking about it tomorrow. But
Okay.
yeah, there are several attempts to do it where you can bypass time steps and go directly 100 time steps, etc. But the problem with most of those methods is that there is an error, finite error, and this starts diverging as you go forward.
In that case, so it's good to have a sort of symplectic structure from the beginning
Exactly.
in the machine learning.
Exactly. I completely agree. I think there are multiple ways to infuse the physics. One is to have a symplectic structure. One is to constrain it on a phase space. For example, if we know the underlying dynamics. So, for example, like, if you're thinking of normalizing flows kind of things, you try to make sure that the distribution that it samples from is always preserved. But I think, yeah, these are interesting ideas to pursue further.
Sarika, a quick one, and then Gilles, and then we move on to the next talk.
Okay, so Anoop, maybe we can discuss later more, but just a question here. Now, when you created these 3 potentials from the same trajectory, right? And you have a WCA and LJ and the Morse potential. Now, if you put in these potentials, the trajectories will be different. So what is the relationship between the potentials, that you have created, which is finally stabilized?
Yeah, I mean, I think this is a very interesting question, and we have not gotten to this in the sense that this is a very recent result. But the point that the way we try to evaluate, I mean, okay, two parts to the answer. First is, what does the learned potential capture? Does it only reproduce the RDF, or does it capture some part of the dynamics, right? We try to evaluate it by simply looking at this particular quantity, which is phase 6, and we saw that other 2 potentials are not reproducing it. I don't remember which one. I think this was WCA that reproduced this correctly. The other 2 did not give you this correctly. So that means that all 3 potentials are not the same. They are completely different, but they are trying to approximate the RDF on which it is trained on. Yeah.
Quick one. Well, first is a comment, so it's very, very quick. I haven't understood how you managed to tame the divergence of trajectories for calculating the viscosity with the Lyapunov exponent. So if you can explain us tomorrow in your longer talks, it would be great. The second one is that when you have pair interactions, you know that there's a uniqueness theorem that relates the G of R to the pair interaction. But we know that for that, you need almost an infinite precision to get exactly the mapping. So, which is impossible in your case, where you can have several solutions. But if you add the triplet correlation functions, that you can also measure the triplet, the 3-body correlation functions, then you will immediately select probably more efficiently the right solution to your problem.
Okay, so I think we move on to the next talk, and
Right. I mean,
let's thank Anoop for this interesting talk.
Thank you.
And, so next talk will be by Ludovic, And yeah, no title is written here. Okay, so Ludovic is going to talk about machine learning classes and their enhanced sampling. And
Yeah, I have mine, so don't worry. What's funny? Okay, they're making fun of me. Okay, so thank you for the invitation. So Giulio Biroli should be giving this talk. So it was supposed to be the part on to where he applies machine learning techniques to glass problems. But we have worked a lot about these things, and I gave the talk about this topic last week. So we said, I'm going to step in. So let's pretend I'm Giulio, and I give the second part of the talk.
And is Giulio going to pretend he's you at some point?
Well, he could. I mean, you know, okay. Exactly. So collaborators are, of course, Giulio Biroli. So I'll be talking about papers that we have written together about problems where we have used machine learning to attack glass problems. So the people were Gerhard Jung, who is now a postdoc in Austria, I guess. He was a postdoc with us, Giulio. And Leonardo Galliano and Louis Greniot are postdocs who are finishing in Paris, and Marie-Lou Gabriel is also at the ENS. Okay? So this is the topic. So we want to use machine learning to think about glass problems. So there are many glass problems. We all know that. So we can think about the crystal, the supercool liquid, the glass transition, the Katzmann transition, the aging glass. We can look at low temperature properties, all of this. So the goal of this machine learning thing is, can we find one of those questions and see whether the machine learning techniques can help really address those questions and make progress that will not be very easy to do without it, okay? So let's make it not clever, but useful at least. So that's the goal. So the first thing that I will be discussing is, can we say something, understand something about slow dynamics in supercool liquids? And can we say something about how easy it is or how difficult it is to sample the configuration space, which is the same thing to me. Sampling is difficult because dynamics is slow, okay? So one part of the talk will be, we all know that the dynamics slows down a lot. It's an interesting physics problems, and we'll be attacking the question of the dynamics, the physical dynamics. And it's also a burden for us doing computer simulations because it means exploring the configuration space is slow because the dynamics is slow. So it's a burden to perform equilibrium and ergodic sampling to measure things in equilibrium conditions. So these are two topics that we'll be touching today. The second type of things is structure of these amorphous solids. So these are, again, taken from simulations that Misaki has done, obviously, for two-dimensional glasses. This is a really high temperature one. This is one that has been prepared with the swap. And by the eye, you can tell maybe the difference if you're Misaki. Far away, it's looking like balls, which are very disordered. So the message from this is that the evolution of the structures, we know as the system approaches the glass transition, evolves very weakly. And it means that if you want to think about the generative models that Giulio was thinking about, you need to be able to predict this and this with different models at different temperatures. So the precision of the generation of the configurations must be huge, and that's going to be a challenge in terms of generating configurations using machine learning techniques. So probably somewhere there's some hidden order, as we discussed, or locally favored structure, point set, whatever. And the generative models have to capture this in order to make the distinction between these two things. Challenge, okay? Second thing, then the connection between statics and dynamics is what Misaki has mentioned before. So this is a bigger version of what I showed you before. This is a configuration that has been equilibrated halfway between the mode coupling transition and the experimental glass transition. So it's still very dense, very disordered, very boring looking. If you run the dynamics to very long times with this system, this is the type of dynamic heterogeneity you see. Particles are colored according to the local relaxation times. So the red regions here, they relax after 10 to the 5 or 10 to the 4.7 MD steps or MD Lennard-Jones steps. And the regions in the dark after 10 to the 10, they still have not relaxed. If you go back to the initial condition, this is the red part, and this is the dark part. Can you tell them apart, is the question. And so apart from Itamar, and nobody else has, so this is the conundrum of this. And yet we know that the structure is dictating the dynamics. So that's an interesting question for us, and maybe for the machine learning techniques, okay? So why machine learning? So these are 4 items where I have seen, and we have reviewed in this global paper that has been written from a workshop organized 3 years ago about what questions can be addressed using machine learning techniques in the field of Laplace transition. So I won't mention work on can you identify the structure, like the question that Itamar has answered by just asking the machine learning models to detect structures or complex structures which are invisible to most of human eyes. Okay? The second thing that has been attacked is, again, we know that when we shear, when we look at low temperature properties, these homogeneous looking configurations give rise to these localized defects, TLS or two-level systems or shear transformation zones, localized plasticity events. Can we look and find and use machine learning techniques to detect these glassy defects? And some works have been going on. So what I want to do today is come back to the question is predicting the heterogeneous dynamics that Misaki mentioned yesterday, and the question of sampling configurations, very much in line with the generation of images that Giulio mentioned yesterday. So these are the 2 examples, dynamics and sampling. So we start with the slow heterogeneous dynamics. So this is a supervised learning problem that Misaki has beautifully introduced. Again, this is the goal. This is the real physical dynamics of a very deeply equilibrated supercooled liquid. This broadly distributed timescale from a fairly homogeneous configurations with fairly extended spatial correlations of the dynamics, which on these 2D systems at very low temperature extend to many particles. Okay, so because we are solving Newton's equations to this long-time dynamics, we know that all the information is stored in the initial conditions. Yes, Paddy?
It's 2D.
This one is 2D, yeah. Later 3D systems, well, 3D systems have been studied not by us, but by other people, and it, to my knowledge, it doesn't make any difference. Of course, the physical dynamics may be different. Okay? So we know that it's all there, so we just look at the initial configuration, and we should be inverted to this. Okay, so this is, again, what Misaki told you yesterday. So the goal is to train a machine to take as much information as possible from the initial structure. The dynamics is used in the training period, and then you use your favorite architecture machine learning model that should learn how to transform these local structural features that you have here into a number which relates to the local dynamics of the particle. So you use actual trajectories for training your models, and once your model is trained, if you're successful, if you're given a new initial configuration, you should be able to predict that label, the long-time dynamics. So that question started about 10 years ago, as Misaki mentioned, in the group of Andrea Liu mostly, and then it exploded a little bit over the last few years. The DeepMind paper 2010-3, I think, started the competition. They said we can do better, so everybody wanted to do better because there was a metric to be. So there is now a diversity of architectures, and at the end of the day, they all do extremely well these days. So this is the conclusion of this. It's really a success in the sense that many, and there are 4 here, different architectures and models, machine learning models, are able to predict the dynamics given the initial structure with fairly good accuracy. So this is a slightly different example of what Misaki has shown today. This is a 2-dimensional ternary Lennard-Jones mixture. This is time. This is the Pearson correlation between the prediction and the actual dynamics that you observe. And the Pearson correlation is something between 70 or 80%. So the best ones do even better. So the overall conclusion from this is it's not so complicated after all to train a model. You give it the local structure, and then it spits out the long-time dynamics with a very good accuracy, and a very strong correlations between prediction and the actual dynamics at a single particle level. So that's success. It at least succeeded into predicting. So I'll go a little bit more into the details of one example, the one that Julia and I have studied with our postdoc Gerhard. So we started and we entered the competition a bit later, so we could sort of use the experience that people had gathered to decide what are the structural features that really mattered in terms of the prediction, and it's exactly the long list of features that Misaki has described yesterday extensively in his talk. So we look at potential energy, local pair correlation functions, and importantly, what we do is we coarse grain over a number of length scales, and we feed everything to the machine learning model. So this is the input. The input is translating the particle positions into numbers that you put into your neural network. Okay? And then Gerhard played a little bit with this multi-layer perceptron. At the end of the day, you spit a prediction for the dynamics. Okay? So what Gerhard has been doing is include more and more of the informations we had on the dynamics. In particular, we were careful at thinking about predicting the spatial correlations of the dynamics, not only single particle, where you have no information on the spatial maps, but we put these spatial correlations into the loss functions in order for the predictions to be as realistic as possible compared to the actual dynamics. So this is an example of what we achieved. So this is snapshots from the molecular dynamics and some early times and close to the alpha relaxation times, in the MD, short times, long times. The color is coding for the local relaxations, and this is the predictions for the machine learning things. And the snapshots look superficially very close. The Pearson correlation function is close, and most importantly, the spatial correlations, the distributions of the dynamic heterogeneity, everything is predicting extremely accurately. So we would say the predictions are extremely close to all features corresponding to the real dynamics of the system. And again, we just feed this for the prediction at the end when the model is well trained. So that, I think, is one thing it's doing correctly. It's really predicting all features of the dynamics, just not one number, but all of them. Okay, so we asked different questions. So these questions were asked yesterday, so I added these two slides to answer some of them. So what about you are training your model at a certain time and a certain temperature? Can you extrapolate the predictions to other times or other temperatures? So we worked hard on this in a subsequent paper with Gerhard and Giulio again. And this is what we did. We collected data for all times and all temperatures that we could, and we now trained the model with everything. It means if we were asking a prediction for any temperature and any time that the model has not been trained on, it could spit a very good answer. So we have made all these tests. We just take a time that has not been seen by the model. Can we predict it? We go into the simulations and we validate that transferability in times and temperature is extremely good. So the reason we wanted to do this is because we say if we train over this temperature range and we can essentially predict anywhere, can we even predict outside of the training regime? Can we extrapolate? And the reason we wanted to do this is because we have those configurations. The swap is giving us these initial conditions. So we did that thing where we extrapolated also in temperatures and times where we have not even trained the model with it. So this is what this cartoon is trying to show. So this is snapshots measured for an initial configurations that equilibrated at the experimental glass transition. We also transferred the system in system size. So this is a 300 by 300 particle size. So it's a gigantic system. The relaxation time being 10 to the 12 here in molecular dynamics units. For such a gigantic systems, we computed, I think in the paper, it would take 10 to the 11 years to just run those simulations. And here we just put the input and the machine learning model is spitting the configurations. I think there is a movie attached to this. So this is the 300 by 300. And you see as time progresses how the dynamics proceeds. This is again a color code for the local dynamics of the system. And this is a system at TG. So we would claim this is what the dynamic heterogeneity would look like if we could do these gigantic simulations. I didn't mention this. We also checked that if you train the model on a decently large system size and then you try to predict the dynamics and the map over a much larger system, it works beautifully. Not surprisingly, because a large system at the end of the day just the superposition of independent subsystems. So generalization in large systems is really good, and that's needed when you want to measure these 4-point correlation functions that require very large systems. And here you have them for free. You can train the dynamics on small systems, make predictions for large systems, and it's beautifully giving you all the multi-point functions without extrapolating anything. So it's really good, we thought. Okay. The second question that Misaki has also asked is, do you learn something? Can you interpret your results beyond just maybe using it as a robot to learn something about the dynamics. So this is one thing that we did, so we can think about the way the model is learning about these structural features. Maybe it's telling us something, okay? So this is the question Misaki asked yesterday. So this is a complicated plot where we have taken all the structural informations that are being fed to the model, and we rank them with respect to this length scale L, which is the coarse graining length, essentially. So you have very local indicators that only know about your neighbors. The L would be 1. And then we have features that have been coarse grained over large length scales, so they are informed about very large length scales, okay? So some features know about a lot of particles, some features are very local. And so what we decided to check is whether the machine learning model is putting more weights on some of them and how this is changing when you decrease the temperature. And this is when you go from red to blue, you see that it's putting more and more weight onto larger and larger length scales. So it's getting information from increasingly large length scales in order to keep the quality of the prediction very good. So what we've been doing, I think we took the integral below this, or the first moment of this, and we have defined, if you wish, a dynamic correlation length that is being extracted from how the machine learning model is using structural features over different length scales. And what we have been finding that this is very consistent with the growth of the 4-point dynamic correlation length. So in a sense, the network with this organization of all the features, it is learning the dynamic correlation length, and you can see it into the weights. The second thing that we've tried to do is also we try to see whether among all these tens or hundreds of features that you put, maybe some of them are extremely important, and that would be serving as an order parameter for the glass transition. So we try to do all these dimensional reduction thing, and we discover that it's true. You can essentially predict very well the dynamics knowing only 2 numbers. So you have these things where the dynamics is really spread out in terms of these 2 order parameters. Then we looked at what these order parameters contain, and they contain everything. Okay? So it means, cool, you can define numbers, but they are meaningless because they cannot be expressed in terms of the Tanaka theta, the density, the something. It's a weighted sum of everything, and everything is needed to get the right prediction. So to me, the conclusion is that at least for that system, there will be no simple form of a static order that can predict the dynamics because it's a big mess. Okay? My conclusion. So I go to the other part. I don't remember when I started, but I don't know. Yeah, I just want to know how long I have for the entire, roughly. I started when? Okay, it doesn't know. So I think you still have at least 15 minutes. I just started. Okay.
Chair is linear.
Okay.
250 you started, so it's, I'm just keeping it up.
Okay. So now we are going to try and generate configurations at low temperature by these machine learning techniques. Okay. So for Luca, I wanted to go back to. Yeah.
I think there's a very interesting question that I think
I'll drink water while you ask.
Sure.
Yeah.
I think there is an interesting question that you're coming close to, but I'm not sure. And this is this. We have many ways to quantify order. Symmetries, stories, blah blah blah. Now we have no way to quantify disorder, and I think that you are now beginning to touch a possibility to really quantify how disordered the system is. Do you think that this may be pushed towards it? Because that would be very interesting, because we really don't have this.
Yeah,
we're talking about disordered systems for decades, and we don't define what do we mean. How disordered is disorder? I'm not sure this is the right moment to ask this question, but I think it's a very interesting question.
It's a very, I agree with everything you said, including the conclusion. It's true that there are some systems and people have, sure. There are some systems for which you look at it and then you have 1 or 2 numbers that pop out that predict the dynamics, and they probably are more ordered according to that metric that you are suggesting. This one, we made sure that it's a really complicated one, like the 2D polydispersed. It's pretty hard to predict based on 1 number. No single 1 number does it, which is your definition of absolutely disordered. Okay, so how do we sample low temperature configurations? Usually we start from the goal, which is produce equilibrium configurations with the Boltzmann distribution. That's the goal, okay? So the dogma that has been around for 70 years since computer simulations were invented, it's impossible to produce directly such configurations because you would need to know this distribution, you would need to know the partition function, then you would have to solve the problem first before, so you don't need the simulation. So dogma producing directly such configuration is just too hard. So we have to go and do something else, and the something else is Markov chain Monte Carlo simulations with detail balance. So the solution is you construct a stochastic process, you jump from one configuration to the next, the two rules that you know, you propose a move with a certain probability, you accept the move with the probability that satisfies detail balance. Look at detail balance means the probability to go forward and backward compensate exactly. Okay? So this is the Metropolis first Monte Carlo paper. They invented this, and everyone has been doing this, because if you have this and this and this is converging to the Boltzmann distribution. So you start nowhere else, you follow these simplistic, stupid rules, and you converge to the Boltzmann distribution without knowing the partition function. This is why Monte Carlo simulations are used. Okay. Okay, so the art, of course, is to make it fast, because if it takes forever to converge, then you did nothing. You have a beautiful method that you can prove converges, but if it's too long, it's too long. Okay? So this is why inventing new Monte Carlo schemes is just a way of speeding up that convergence. Okay, so if you look at the acceptance probability, so this is the proposition of a configuration. This is the acceptance of the you see that if you could propose a configuration that directly samples the Boltzmann distribution, that term here would just cancel out. It would be 1, so all the moves would be accepted. It means you would have killed the dogma. You would have been producing directly configurations. So if we could do this, then we would accept all configurations, and the convergence time would be 1 because the next configuration is very good. This is what the machine learning people are selling us. They are trying to say we can do this. Okay? Okay, so this is how it goes. So it's all start from the talk of Gilles, generative model. You start from noise, you do some tricks, and then you generate your cats and your dogs. Out of the noise, you generate meaningful figures. Okay, so the key difference that I want to tell you is that it doesn't have to look like a guy, it has to be a dog. Okay, when it comes to sampling the Boltzmann distributions, you have a hard constraint that you need to sample the exact Boltzmann distribution. It's not about the Boltzmann distribution, it is the Boltzmann distribution that we want. So the example that I have in mind is, imagine that you could produce a hard sphere configurations that looking like one, but in terms of these gigantic configurations, you have two particles that overlap by 10⁻⁶ of sigma. It's a forbidden configuration. So you make a small error, the configuration is forbidden because it doesn't sample the Boltzmann distribution. So errors are forbidden. Okay? And hence, producing about dogs or Boltzmann distribution sample configurations, it's way more complicated. Okay? It's a different thing. So in this normalizing flow paper by the Unifying group, this is what they do. They start from noise. They invent a transformation to sample the Boltzmann distribution. It's looking like one, they do the thing. So this is the Boltzmann generator. So this is the science that handles gigantic proteins. In the paper next year, they do particle system that we like with periodic boundary conditions and symmetries, etc. They handle 2 Lennard-Jones particles in the external potential or 13 Lennard-Jones particles. So it's telling you that sampling a configurations in particle system is very complicated. So this is a subsequent paper. They do 32 particles of a high temperature Lennard-Jones liquids because you have to handle the periodic boundary conditions, the symmetries, translations, and rotations. It's not so easy. So the idea is you want to start by producing essentially noise or very high temperature configurations, and you want to transform them into good configurations. And of course, the art is to learn this transformation. And you hope that at the end of this transformation, this map, you're sampling the Boltzmann distribution. Okay? So to be able to use the produced configurations, you have to be able to understand what distributions you're producing with your machine learning models. Because if your model is not exactly the Boltzmann distribution, to do Monte Carlo simulation, you would have to reweight using this. Okay? So if your probability is almost the Boltzmann, but not quite, you have to filter and use detail balance to do proper equilibrium sampling. Okay? So hopefully you hope to learn the Boltzmann distribution or very close approximation to it, and then you would achieve the direct sampling method that I mentioned before. Okay. So this is what we do. So we, with Giulio and Gerhard, we used the architecture developed by the NOE group. It's called continuous normalizing flow. And this is a way to essentially parameterize this transformation between the high temperature and the low temperature. So the way it's constructed in a few lines is the idea is to learn a vector field V of x and t, and this is how the configuration x is transformed between time 0, you start in the initial configuration, the noise, and time 1, and you hope this is the Boltzmann distribution, by solving these very simple equations. Of course, now all the complexity is in the vector field. So vector field, they represent a sum of pairwise potential, and this is where you have all the parameters of the machine learning model. So all the complexity is to learn the model, to parameterize this, to solve these equations, to transform the configuration, roughly speaking. Okay? And because the interest of this equation is that given the initial distribution and the velocity field, you can get the distribution that you're actually sampling. And then the goal is to have that distribution very close to the Boltzmann distribution. If you can do this, you have direct sampling. Okay, so you train your model, you learn your things in order for this distribution to be as close as possible as the Boltzmann distribution. And then if you are successful into the training, starting from the high temperature liquid, you produce low temperature ones. Okay? So this is what we did for this first paper. So we took 43 particles for the two-dimensional same ternary Cobb-Anderson system. And what we measure is essentially what is the predicted average potential energy compared to the true equilibrium one that we know because we have the swap. Okay, so if we do molecular dynamics, this is equal to 0 because the predicted or the measured potential energy is equal to the equilibrium one. You decrease the temperature and the system falls out of equilibrium. Now we use the continuous normalizing flow and we can maintain equilibrium down to a temperature that is considerably lower than the molecular dynamics. That means that clearly the direct sampling method that we have, it's outperforming molecular dynamics considerably for this very small system size of 43 particles. So there are two problems that I would like to address in the minutes. If we go to slightly larger system, 3 times larger, the scaling is not really favorable to N, because then for this system size, the normalizing flow and the molecular dynamics are essentially equivalent, so we stop gaining anything. So the scaling with N doesn't help. The more, I think, problematic thing is that when we look at the transformation that has been learned here, the velocity field that transforms one configuration into the next, we find that velocities are typically extremely small, so the particles essentially don't move. Okay? So you don't so much transform the configurations. Instead, what we think is happening is that we're able to select the good ones from the prior distribution. So we kill the bad ones, we kill the good ones, but we don't really produce anything new, which is not what we want, because we don't really learn anything, or we cannot really generate new configurations. Okay? So this is what we were, where we were. Okay, so people have been developing these machine learning techniques. So there is a refined version of the continuous normalizing flow. It's now called stochastic interpolance. So the idea always relies on this velocity field that's being used to transform one configuration to the next. But the way technically it's being trained is slightly different. It's way simpler, and then it works much better. So maybe in the interest of time, I have to skip how you exactly learn this, but the idea is you take one configuration at low temperature, you take one configuration at high temperature, and you invent a stochastic process that interpolates linearly between the two. Very stupid one. It's so stupid that you can use it to train and parameterize your velocity field. And the loss function is also very simple. So everything is becoming a bit simpler. And so again, the strategy is you try to learn the velocity field, a transformation, and you minimize your loss function by adjusting all the parameters as usual. Okay? But here, of course, you have to have samples at high and low temperatures, and you have to do this interpolation. After training, what you get is you get the velocity field, and you are back to what I was doing before. So you have a new transformation that goes from 0 to the end of time. And then you get your distribution, so you can check and sample the equilibrium sampling. So at the end of the day, it's looking like a continuous normalizing flow, but the way to train it and parameterize is slightly different, relies on a much simpler stochastic process. And this is what people have been doing. And this is the work that Louis and Leonardo have been doing. So first of all, in order to study the type of particle system that we like, they had to make this model, rotationally and translationally invariant. They had to make also the case that we have different species in our system in order to, from these configurations that have been generated by Monte Carlo simulations, try and generate new ones using these transformations. And the success of this, to me, is that we start from totally random points in space. So we start from stupidly infinite temperature configurations, and this is what we get at the end of the process. So the model truly transformed the particle. It's moving the particles around to remove the overlaps and organize in space and hopefully capture this subtle glassy order that we are all talking about. Okay? So this is, so you take this configuration, this is the pair correlation function you get directly from the model, but now you use your Monte Carlo detailed balance algorithm, so you reweight and you perform a Monte Carlo of this. And on this, you have two lines, the true G of R and the one that has been predicted by the model. So for this particular system and these particular sizes, the direct sampling works. I can directly sample configurations, and I choose and reweight them with the Metropolis algorithm, and then the correlation time is 1. Okay? So this is, in a sense, success. Of course, it's no miracle. We have used the data. Okay? So it's not sampling from out of the blue. We have used real data generated by Monte Carlo in order to not use Monte Carlo. So this is a relatively high temperature liquid near the onset, I think. So this is the final slide of this. I'm done. This is the final slide, okay? So this is the ternary Cobb-Anderson system, so 3 colors. This is 44 particles, and this is configurations that have been produced by the SWAP Monte Carlo simulation, so considerably beating the molecular dynamics, of course. These are the configurations generated by these stochastic interbalance normalizing flow things. They look okay. If you count how many fingers the people have, it's not quite there. So it's looking decent, but it's not yet the Boltzmann distribution. So it's slightly out of the range of the Boltzmann distribution, but it's very close. So if we could finish this, and these two guys, of course, have finished their PhD, right? If we could push this a little bit, it means we could, in principle, produce just instantaneously very low temperature configurations for that system, and then hopefully use it for sampling glassy configurations at low temperature. So I try to say there are many questions in glass physics where you can think about use machine learning techniques to address physics questions that we care about, that are difficult to address, and maybe machine learning techniques will not solve the problem, but help us solve it. And this is, of course, indications. So I fed ChatGPT with all the keywords of my talk, and this is what it spat.
Let's have Ludovic. So,
I can explain all the small details. There are many details in it. It's beautiful.
okay. So we can have a quick 1 or 2 questions. And
so in this velocity field, can you somehow build the detail balance like in Monte Carlo?
Why would you do that?
No, I mean, then at least, I mean, I don't know. I mean, detail balance sort of ensures that you generate with.
Yeah, but the goal is not to use anything physical. The goal is to use something stupid, noise, like in the generation of images of Giulio. You start from random noise and you want to, infer a process that is going to transform that noise into something meaningful. So you don't want to use the physical dynamics because you're trying to bypass the physical dynamics. So I would not go into the direction of making it too physical, because then you'll be doomed.
Yeah, but like instantaneous, I don't know, instantaneous detail. I mean, like you do a transformation, but like swap Monte Carlo. But
so to me, the way these people think and the way the models are constructed are probably avoiding going back into these nightmares. So the goal is to be totally fresh and arrive and find transformations where, again, the goal is you need to be able to parameterize this transformation in a multidimensional space, not easy, and you need to be able, at the end of the day, to know what probability distribution functions you're sampling, because this is what you need in order to do Monte Carlo simulations with the Metropolis acceptance rule. So all the constraints point to you should not use physics, you should use these multidimensional things. You should learn from the machine learning community how to do this very, very efficiently, and then apply it to the physics problems I think.
A quick question on your first part. When you do the extrapolation to other temperatures and times, do you feed those parameters explicitly into the network, and how do you do that?
Yeah, so I tried to read it last night again to remember how we did it. Yeah, we have a way to sort of tell when, during training, we inform the labels, they know about the temperature and the time, so we feed that into the data, and then there is a way there is an attention layer, I think, that gives weights at different times and different temperatures. So we would have to look at the papers together again.
Okay, thanks.
But yeah.
So I had a question where you assign the weights and see that as you lower the temperature, the weights shift to the ranges of, this plot. So does this mean below a certain temperature, the relevance of, say, the length scales that correspond to the nearest neighbor or something doesn't matter at all?
Well, it matters less. So it's just that it's the relative weight between large length scales and small length scales that's being shifted.
By that I mean, if you had the information of just, say, the length scale corresponding to 2 to 6.
But you know what to do. I mean, if you truncate like this, the quality of the prediction would degrade if you decrease the temperature, simply. Okay. So if you keep a finite L for all the predictions, you would do great at high temperature, you would do worse at low temperatures, because you need that information to keep the quality constant, in a sense.
Okay, thank you.
Ludovic, I have a question exactly on this slide. So if you look at dynamic heterogeneity and or particle displacement, and then coarse grain it, then you can show that the Van Hoff function will not show exponential tail. It will go from exponential tail at small length scale to Gaussian behavior. So that's like moving into a white noise type of behavior. Is this somehow that information getting into here?
No, because remember that what we predict here is the propensity. Propensity means I'm trying to predict the dynamics average over many trajectories starting from this. If you looked at the Van Hoff distribution for the isoconfigurational ensemble, the tails are not there.
They will have the tail, yeah.
So you don't have to predict tails because they are not there in the data. Okay, they are there in individual trajectories, but not in the data.
But just the fact that it picks up that same dynamic heterogeneity length scale, as you go to lower and lower temperature, you need to coarse grain to that level. It's telling you that you go from non-Gaussian distribution to a Gaussian distribution somehow. And
well, I would have to explain. There are many confusions in your question, so I don't have time to clarify all of them.
So maybe I should thank Ludovic, and then we move on to the last talk by Gilles on this is an overview talk, and it will be slightly long talk.
And boring.
No.
I hope. I'll try to shorten it.
Do you know how to handle the screen and the full screen and the slideshow in Max?
When you, I guess I know.
Non, mais la semaine dernière, ça n'a pas marché. Il faut un Mac expert.
So here, so in your case, it wasn't swing here?
No, but last week it was swings, and then you have to go into the... But let's see how it goes. Just going to ahead.
Oh, no. Command L was not the right one. This is pretty nice.
Pinaki, you have a Mac or not? You have a Mac? Can you help him? Like the slideshow, I think it's... I never know where it is in Mac.
Yeah, the slideshow is...
Come here.
Thank you. Thank you. Maybe I should... yeah, that's... Oh, maybe... No, it's not in here. No, it's... Yeah, it should be some bar. It should be some bar. It should be easy.
It should be easy, yeah.
Can you hear me? Even if you... Oh, yes. Can you hear me through the mic, I meant? We're getting there. What?
You don't need the presentation to talk, right?
This one? This is okay, right?
Yeah. This is. No, it's going by itself. No, okay, great. Oh, someone else is.
Okay. You can start.
I can start. Okay, yeah. Nice introduction. Yeah. No, so, thank you, Smaraji. It's okay. So this will be an overview about the mean field theory of glass and formation and beyond. And just one thing that we should, I mean, not for the young ones, but we can point is that, you know, in many of the previous Unifying Concepts conferences, the mean field theory of glasses was dominant in all the presentations. Now you see that in this one, there will be, you know, very few talks related to mean field and beyond. So this is, you know, telling something. I don't know what, but I think it's at least timely to do some kind of assessment and overview of this theory. Okay, just let me remind you of course, many of you know, but I guess this will be useful anyhow, of what is the mean field, in a nutshell, what would be the mean field theory of glass formation. And okay, the idea is that comes back from way back, Waldinus, Kirkpatrick, and Teromolai in late 80s, is that glassiness is associated with the properties of the underlying free energy landscape. Okay, and these ideas come originally from analogies with mean field disordered spin glasses, like the Potts model, the P-spin model. And then, of course, more recently, and what's interesting, we're done from particle systems. So in this picture of the landscape, you know that there is two transitions. There's one transition, which is the dynamical transition at which the relaxation times diverges in mean field, which is, you know, mode coupling like. And below this transition, you have the emergence of an exponentially large number of metastable states that trap the system. And you have then associated with the exponentially large number a configurational entropy or complexity, which is extensive. And then you have a second transition, the Kauzmann transition, which is a transition which is static in that case, so it's in the Gibbs measure, and which then you have formation of an ideal glass. And at this transition, the entropy, configurational entropy, vanishes. Okay, so this is the idea. When this was actually appealing in the 80s is that it had, you know, in the same idea and framework, both the mode coupling theory that was, you know, very prominent in the 80s, and the Kauzmann transition, or the Kauzmann paradox about the configurational entropy, that was also very important at the time, and it seemed to bring together those two ideas. What is it? It means that the number of metastable states is of the number. So it means that the number of metastable states decreases. That's just the configurational entropy decreasing. So you miss metastable. Whoops, this is weird stuff here. Let me just. This is nice, but yeah. So this is okay. So as I said, there was This started from those disordered spin models, but as you know, the mean field theory has been developed also for liquids, especially for liquids in infinite dimensions. And what is interesting here is that we know what's the order parameter of the glass transition in mean field. So the order parameter is the overlap, which is a similarity between two configurations. Because basically, if you're in the same basin, the configurations are close. If you're in different basins, the configurations are far apart. So similarity is the order parameter. And actually, this order parameter is the true one in mean field. That is, it's discontinuous at it's a static glass transition at the Kaufman temperature. And what has been put forward also is that you can build free energy, an interesting free energy, which is the Franz-Peirezi potential as a function of the overlap, which is the free energy cost to keep one configuration at a given overlap with a reference configuration. Okay, so this is important because, again, you have a reference configuration. Of course, all reference configurations are equal, so you will do some quench averaging to get this quantity. But it means that, again, if you're at very small overlap, you're in the liquid. If you're on the non-zero overlap, then it means that you will be localization, and the system will be in a glass. And what was found is in these mean field models is that this Franz-Peirezi potential is convex at high temperature, then starts to develop a non-convex shape, and the moment at which you barely start to see a second minimum, which in the Landau picture is the spinodal of your system. So the spinodal of the system is actually the dynamical, where the dynamical transition takes place, or the mode coupling transition takes place. And then you have a second glassy minimum that appears, that becomes deeper and deeper. And when the free energy of the second minimum becomes equal to that of the liquid, well, you have a first order transition, which is precisely Tk, and then you have a jump of the order parameter, which is Q. Okay, so everything here is, again, mean field. It's like exactly a Landau picture of the glass transition. And what is also interesting is that this picture, brought some ideas of how you can bring in, which is always used in statistical physics, additional external fields. So, for instance, you can induce, you see if this one is tilted, well, you see that if as usual, you add the equivalent of a magnetic field that is linearly coupled to the overlap, well, you will tilt this minimum, and then you will make this minimum just at the same level of the other, and you will induce a first-order transition even at this temperature, okay? So this is the field, which is called epsilon in the literature, not H like a magnetic field, that is linearly coupled to the overlap. And this gives rise to a phase diagram in temperature and epsilon, where you have Tk, which is here, but at higher temperature, you can have a line of first-order transition, first order but not random first-order transition, okay, with a difference that I will explain. And then it terminates, as usual, in a critical point, and critical point. That what you can do, what was done by Chiara and Giulio, is that instead of adding a uniform, say, magnetic field, you can just, in your configurations, pin, so quench, a number of the particles. So you a fraction of the particles. So you have an equilibrium configurations, you pin a percentage of them, and then you look at the thermodynamics of this pin system. So now the control parameter is the fraction of pin particle C, and what has been shown, again in mean field, is that you start from the same diagram at zero pinning, you have Tk, and at higher temperature, then you have a line of now random first-order transition, so there's a transition at which the complexity vanishes that also terminates in a critical point. Okay, so these are things that I think nobody would have thought of if we didn't have a mean field solution, is that how to add those external fields. Okay, so the main point, so far this is nice, but I think, at least to me, what was really striking is that the whole scenario here, is exact in liquids in infinite dimensions. Before, basically, we could poo-poo the fact that, yeah, it's an analogy with the Pod's glass. Yeah, the Pod's glass, This is not like orthotrophenol or even Hartsfield liquids. And so it was something that was very debated. But, when the solution was found for the infinite dimensional liquids, it means that it has to be taken seriously because, again, in statistical physics of transitions, we know that when you have the mean field transition and the mean field description, this is usually the right starting point to then add, of course, a little stuff about it, but this is usually the good starting point. So here, we know we have the proper mean field theory, which is exact in infinite dimensions. It has been done by all those guys here. And for, you know, if students or junior people want to learn about it, you know, there's a book, which is Theory of Simple Glasses, that was written by Parisi, Urbani, and Zampani issued in 2020. So you have lots of things of the solution in this book that I will not go over. The interest of this exact solution on top of being that for liquids, real liquids and real glasses, even if it's in infinite dimensions, is that it makes prediction for a lot of things. So the glass transitions, okay, dynamical, static, the glass phase itself makes prediction for aging. It makes predictions for the jamming point, which of course is something that was very important to understand where the jamming point is located in the whole phase diagram of liquids and glass-forming liquids. It makes predictions for the rheology of glasses, and all of this in a unified framework. So this is, I think, again, to be stressed again as you know, a very impressive achievement, and you'll find again all of this in the book. Now, because we want to go beyond.
Now, what are the most definite things one can say about the upper critical dimension for jamming?
Okay, so I just addressing this, but let me precisely give the, because you read this one, but I haven't told it, so you're jumping ahead, you know, I should do one item by one item, you know, just, you're distracted. Okay, so this is an important point also, on top of jamming, which is that even in mean field in general, is that the fate of the mean field predictions, when you go to finite dimensions, because we are interested by 3 and 2, of course, need not be the same for all those predictions. Okay, and this is something very generic, is that the mean field has a unified framework, but the way it works in finite dimensions may depend on the prediction itself. So we know, for instance, that if you sit at the critical point, then the mean field prediction will be qualitatively wrong, but for many other predictions, it will be okay. And here, precisely the idea is that the prediction, as you know probably, for the jamming transition and the exponents related to the jamming transitions seems to work extremely well for hot spheres and related potentials. Seems to work extremely well from infinite dimensions down to 2. Okay? So this is an empirical fact. The problem that Sri is mentioning, and I wanted to point out also, is that it works very well empirically, but what that means for those who have notions of critical points and all, it means that if it's true, it means that 2 is the upper critical dimension of jamming, above which the exponents are given by mean field. Problem is, you know, the theoretical arguments for saying that the jamming transition has an upper critical of 2 is virtually absent. Okay? There's a very recent work by Jim Thethna and co-workers trying to claim that the rigidity transition has an upper critical dimension of 2, but you know, this is really not super strong prediction. So this is, if you want to work on this is a nice problem to show, and many people have tried. It's not that we're discovering it, okay? that the upper critical dimension of jamming is 2. But here, I will not discuss this. Okay, Silke? Yeah. Yeah. Yes. Right. So, exactly. So here we're taking just again the liquid thing without friction and putting it in all places of the phase diagram. But you're absolutely right. I mean, there's a whole. I don't want to discuss jamming, but you're completely right about all the weaknesses or considering.
That I think all of this confusion comes because you're talking about unjamming. Jamming is the hard sphere solutions disappearing to me.
Yeah, but still there is friction. There's the issue of friction and stuff like this, which is.
Forces don't matter until you're jamming.
Yeah, well, yes, yeah. On soft, yeah. That's what Bulbul is saying. That's what Bulbul is saying. Is that if you come from one phase, it doesn't matter what exactly is the potential, and which is what is found in mean field.
Can I keep this for discussion?
But I don't want to discuss jamming. Okay, this is not my point.
Let's get into
we can have another session on jamming.
Yes. Okay, please.
Can I?
Please proceed. Yes.
So as you see, you should read my items. That's why I see here. I consider more specifically predictions for glass formation. Glass forming liquids in physical dimensions. Okay, so, but you're right. There's discussions about everything else. There's discussion. Let me mention this because there is a special request by Patrick Charbonneau that the rheology of glasses, for instance, it was shown in mean field that whether you uniformly shear or you do active shear, whether you do it at the particle level, where this is the same, you have a mapping between one and the other. So, okay, there are lots of things that can be discussed about the mean field. And here I will only focus on glass formation and glass forming liquids, all right? Well, if we have time, we can, maybe I'll finish before my hour. So if we have time, we can just improv on the other aspects, but let me just discuss this one, if you don't mind. Okay, so we want to go to finite dimensions. Okay, that's the whole point. And again, this is a kind of standard statistical physics problem. I have the mean field description. I have the Landau description, Landau-Ginzburg descriptions. How do I go beyond to describe three-dimensional or two-dimensional physics? Okay. And then what happens is that the mean field, as you know, it's something where you have a local degree of freedom, which is basically in the field of a uniform background. So what you overlook is the spatial fluctuations in the system. When you go to finite dimensions, then you have to worry about spatial fluctuations. But the question is, what are they? If you have a ferromagnetic Ising model, just ferromagnetic model, well, then you have the local magnetization, and basically you're interested in the fluctuations of the local magnetization. And, the fluctuations can be short-ranged, intermediate, long-range, or scale-free. That's kind of trivial. It's just the range of the perturbations. So in our case, for instance, short-range perturbations would mean introducing the liquid structure. Okay, so the G of R of the liquid, which is not the same as the G of R of the infinite dimensional system, which is just like a gas, an ideal gas G of R. In the liquid, we know it's not the case. There is a local structure, and this can be should be introduced. Or if you think of just finite connectivity, which is something also which is known, is mean field, for instance, happens for fully connected networks. But a way to be closer to real life is to consider a finite connectivity with a finite number of neighbors. So these would be fluctuations, short-ranged, that do not qualitatively change the mean field predictions at long distance, but change, of course, non-universal quantities. And this is, of course, extremely important to introduce them. Then, as I said, you have intermediate scale-free, and this is usually what is described by renormalization group, effective theories and all, and I'll discuss this briefly. Now, those perturbations also can be either perturbative. So for instance, you start from infinite dimensions, so 1 over d is 0, and you say, okay, will add one corrections in 1 over d squared, 1 over d cubed, and so on and so forth, and that will be in perturbation, okay? Or they can be non-perturbative, and that's been discussed already this morning. For instance, nucleation, when you are in the region of a first-order transition, you know, the Landau theory tells you that you're stuck, for instance, in a metastable state. You will never reach the stable one. And we know it's not true because you can have nucleation. So the nucleation process is a non-perturbative process because it requires a rare event. And the rare event is just the nucleation bubble or droplet. And in terms of field theory, this is described in terms of instantons that were discussed this morning by Peter. Okay, but the fluctuations there can be those of the local order parameter, which it would be in a simple ferromagnetic system. So in our case, the local order parameter is the local overlap, so that would be some kinds of fluctuations, but it can be related to something else, right? So they can be local order or locally preferred structure, something that Patty and I like very much. You can have all sorts of localized defects that are not included in mean fields, or you can have new mechanisms like dynamic facilitations that I will discuss later. Fluctuations, again, may have a quantitative effect or a qualitative effect, okay? And, you know, many of them, it's just quantitative. As I said, you introduce a little bit of liquid structure and you will better describe some of the non-universal features, but you will keep the same critical exponent, for instance. Here what happens is that, in a sense, the universality class of the random first-order transition scenario with these two temperatures is kind of fragile. I mean, it's a very wide class. That is, you find not only liquids in infinite dimensions, but you find disordered spin systems, as I said, the Potts glass, the p-spin. You find the random Lorentz gas, and you find many other systems that are considered in other areas than physics. So it's a very wide class, but on the other hand, it is based on the concept of metastable states, which is something which, as I will discuss, is very fragile to the existence of fluctuations. So for instance, fluctuations may completely wipe out the mean field glassy scenario. And we know this is the case in two examples. Precisely disordered spin glass models, like the Potts glass in 3 dimensions, where it was found that there is no glassiness at all, or there's a continuous spin glass transition, like in the Ising spin glass. Okay? So very different from the RFOT mean field scenario. And there's also the random Lorentz gas in 3D, where you have a continuous localization transition, which corresponds to a percolation transition, and which is, again, is very different from the mean field description of the random first-order transition. Okay? And in this case, we've shown that this can be related, in fact, to short-range fluctuations. In this case, Patrick Charbonneau and Gilles showed that you might have non-perturbative corrections destroying the mean field RFOT scenario. Yes?
Are these, in a sense, in these two models, are there then, can they be thought of in an RG sense of something, there are relevant perturbations that are driving it away from the RFOT to something else, or
I don't,
that's not
okay, from what I know, and there's, you know, work is limited on this. From what I know, oops, sorry, this is not what I needed. From what we worked on, as I said, for the kind of the Potts glass, for instance, just short, I mean, you bring the system on a beta lattice with finite connectivity, and this destroys the RFOT transition. And in this case, in the random Lorentz gas, Patrick and Gilles found that they were, for instance, instantaneous and non-perturbative corrections that would be hard to obtain through RG. So all of them, RG will not be necessarily the better or the best technique to handle this. Okay, so well, not that I know of, because again, the Ginzburg criterion is in the simple case where you know that the fluctuations that are important are those of the local order parameter, and on a scale that varies the same fluctuations that will vary from being short range to being very long range. And the Ginzburg criterion tells you that, yeah, there is a crossover at which you can no longer forget the long range fluctuations. You have to take them into account. But here, it can be very different. That's the idea of what I'm trying to say here, is that the usual way of thinking about fluctuations, the RG way or the Ginzburg criterion starting from a Landau description, is not necessarily very successful here. People have tried, but it's not necessarily successful. Okay, so the idea is that, as I said, that's something which is rigorous, is that even if some kind of mean field scenario survives in finite dimensions, which I will discuss, is that we know that infinite lifetime metastable states cannot survive. So in finite dimensions at non-zero temperature, there is no metastability. Okay? This is a general theorem. Of course, there is no metastability on infinite times. Okay? If you wait, if you're an experimentalist, you can find metastability, but it's because your observation time is not infinite. But at least in statistical mechanics, rigorously, there are no metastable states. And as I said, metastability and the exponential number of metastable states are at the core of this description, mean field descriptions. So this explains why it can be very fragile. So the upside is that, of course, TD is a little too high, as it doesn't have the right features of the phenomenological glass transition in actual systems. So it's nice because it's telling you that you're not really blocked or frozen at TD, but that you can have relaxation at and below TD, like in real supercooled liquids. And this will go through different mechanisms. And of course, as I said, the downside is that metastable states are at the core of mean field transition. Now, there is, of course, a phenomenological extension it's started by Wallinus, Kirkpatrick, and Thermoli, which is, has been called the random first order transition theory. So the random first order transition in those systems is really what happens at TK. So it's the static one. But, we also use random first order transition theory to mention the extension of the strictly mean field description to try to describe three-dimensional liquids. And so what happens is that, as I said, there is a nucleation argument, which is very natural if you think of ferromagnetism at low temperature, is that you cannot be stuck forever in a metastable state, and the easier way to go from one to the other is to nucleate something with a competition between interfacial tension and a driving thermodynamic force, which usually is the difference between potentials, Gibbs potentials in standard nucleation. And here will be precisely the configurational entropy. Okay, so the configurational entropy is the driving force for nucleation, the fact that it's non-zero. Then from this, okay, a nucleation argument, again, Kirkpatrick, Thermoli, you can infer something, again, it's very reasonable, like in nucleation, that the log of your relaxation time will go like your free energy nucleation barrier, which can be described in terms of a length scale. And so it will grow like a length scale to some power divided by the temperature. It's an activated process because it's a rare event. And you just go over the barrier through thermal activation. And this will be, you know, a growing length scale, and this will be the, if you want, the activation free energy. More rigorous is the 0.2 set length, which is the length, as I said, there's a time scale for defining metastable state, but in a way there is also a length scale. And this is interesting, is that, and it's the length beyond which, so if you go to larger length scales, below this length, you can no longer define metastable states. So shorter lengths you can, in some sense, but beyond you cannot, okay? And this is an argument was given 20 years ago now by Giulio and Jean-Philippe Bouchot, is that you have, and it, you know, something again that looks like competition between interfacial tension and the entropic drive. You have a length beyond which you can no longer define metastability, but this is a length that grows as you decrease the temperature because the configurational entropy decreases. And, well, this can be made a little more rigorous, and it's called, I always say it, but it's called 0.2 set because it's a correlation between, say, the center of a point and a whole set, which will be the boundary here, because this length can be measured. And this is important for 3 dimensions and 2 dimensions, is that you can measure this length scale, which is an equilibrium correlation length, and you can measure it through the cavity construction. Just briefly, I recall that you take an equilibrium configuration, you choose a cavity somewhere, you freeze the outside in the equilibrium configuration, and then you re-equilibrate inside, and you look at the crossover behavior, you know, related to what I said, that you have metastable states or no metastable states, the crossover behavior that will define you the length. There is a way to measure this length in finite dimensions. And then more generally, you know, if we don't want to stick too much to the nucleation argument of Kirkpatrick, Thermoli, and Woolliness, you know, it's reasonable that if you have a length scale, which is a correlation length, that you will have relaxation on this length scale. And since we are, you know, pretty stuck in metastable states, that this relaxation will be activated. And so it will go, the free energy barrier will go that this length scale to some exponent, which say is maybe unknown, but is to some exponent. So this is also stuff that I will come to. All right, so I said going to finite dimensions, we have the 0.2 set construction. We could check for activated stuff. What one knows is that the dynamical transition, because it's related precisely, it's a spinodal. So it's where, you know, it's something which is directly related to metastability. So this can no longer exist in finite dimensions. So we know that there is no mode coupling temperature in finite dimensions. It's been known for a while, but here it's rigorous, and it can at best persist as a crossover. And we know it can be due to, the disappearance can be due to thermal activation or even to disorder-induced fluctuations, something that we did with Saroj actually a while back. We can also define overlaps, of course, locally, and overlap fluctuations, and thermodynamic transitions in the presence of applied fields, random pinning, or as I said, the equivalent of the magnetic field. So this can be defined in finite dimensions also. So we can really test, you know, what remains of the mean field scenario in finite dimensions. So it was just the introduction. It's good. Yeah, I'm good. So I will focus, as I said, on 3D and 2D systems and through computer simulations. So the reason I'm saying computer simulations and not experiments is not because I want to piss off my experimentalist friends, but it's because, in fact, and this is the weakness of the theory, there are not enough constraints coming from the comparison to experiments, because there are too many ad hoc parameters. The interpretation is never unique. So the information, I mean, plausibility is there, so you don't want to contradict the experimental data, but we have enough flexibility with many of the theories of glass transition that we can always fit the data, okay? So this is why comparison to experiments is not enough constraining. I will do first static quantities and then more interesting, the dynamics. For first, and I think this is something that has been known, is that the 0.2 set correlation length has been.
But I guess one could ask, are there more measurements that could be suggested from the theoretical analysis that constraints?
Yes, okay, so, right. So, I mean, maybe I can answer now. So sure, I mean, we know there have been experiments on colloids, random pinning, for instance, and you did pinning, didn't you? Yeah, that may be helpful. You know, again, it's not very much clearer than in a computer simulation. And then what has been suggested is, of course, the nonlinear susceptibilities and what have been measured, you know, the 3 omega, 5 omega, 7 omega by François Ladieu and co-workers, which show something. So it's not that there is zero possibility. It's just that, A, it's very, very hard, and second, as I said, the interpretation is never truly unique of what you're having. But yes, okay, so just to say here that there is clear evidence from the, again, cavity construction and others constructions, that there is indeed a 0.2 set correlation length, and this is something that is non-trivial again. You know, it's not something that people would have thought of before the mean field description of glasses. There is a 0.2 set length that grows as temperature decreases, and you know, the growth again is as we would say, we used to say, or we still say, is modest. So it goes from a factor, basically a factor of 3 over the range that you can measure, even with the swap, of course, because the swap algorithm is very important to equilibrate at lower temperature than one used to do, and maybe 6 in the case of two-dimensional systems. So it is significant, but it's not like at a critical point where you would have something, you know, that grows by a factor of 100. And there is a concomitant decrease of configurational entropy. Okay, so these are facts. Now, the second point I wanted to stress is that, you know, I said that some of these systems, when you go to finite dimensions, you destroy everything of the mean field glassy behavior. Well, it's not the case when you look at liquids. So this is again a non-trivial result, is that when you go to liquids in 3 and 2 dimensions, if you're able to suppress some fluctuations, you will find something that is very reminiscent of the mean field behavior. And the way to suppress fluctuations is to take a small system. Okay? If you take well, maybe it's a bit technical, but if you take a small system, of course, you're restricting the fluctuations to the size of the box. Okay? You cannot go infinite range, except for the zero mode. Okay? So there's a subtlety, which is you restrict most fluctuations except those of the zero mode. So depending on the quantity you look at, you will have something that looks like mean field, including non-convexity, or you will have something that will round the transition, which is due to the fluctuations of the zero mode. So there's something a little, it's interesting, but there's something to think about. So it turns out that the transparency potential, which considers the overlap, freezes the zero mode by construction. So in that case, what you find is that indeed this is 3D hard sphere mixture. This is what we did with Benjamin Gilles and Ludovic. This is 2D and 3D. So you see that in small systems, for the V of Q, you get a non-convex free energy, which of course should be forbidden due to fluctuations. But because we freeze the fluctuations of the zero mode and we restrict the fluctuations of all the other modes, we get indeed this kind of non-convex behavior, exactly reminiscent of mean field. Okay, so this is kind of a nice example where we find remains of mean field. Now, another one that will be discussed tomorrow in Ludovic's second talk is you have also in small systems, you have evidence for Kaufman temperature when you can go to lower enough temperature. And again, it's the same idea. You know, you can, in a small system, this is again the Franz-Parisi potential, you can be non-convex, and you can find in that case you go even lower by using not only swap but parallel tempering, population annealing, more tomorrow, and you find that there is indeed something that looks like exactly the mean field prediction, but in a small system. And I explain why you can find this a small system. There's also evidence for this for random pinning. Now, this is small systems. Now, if we want to go to the thermodynamic limit, now this is a little more complicated, but what can be done is what was done by several people, but we worked on this with Ludovic and Giulio, and is that you can look at, you know, again, when you add, for instance, this uniform field, and you find actually that in that case, even by doing the thermodynamic limit through finite size scaling, so in that case, we're really taking care of all the fluctuations, including those of the zero mode, you find evidence for phase separation and for a line of first order transition terminating in a critical point. So again, this is something which was predicted from the overall mean field behavior and is non-trivial. And more than that, we can also show that through finite size scaling, again, so you're changing the size of the system and looking at the critical behavior of the terminal point, and we can find that as we predicted, the terminal critical point of this first order transition line is in the random field Ising model universality class, my favorite model. Okay, I just describe it, but I think it's of no interest for those who do not know. What is interesting, at least got us excited for a while, is that there is some kind of mapping between the statistics of the overlap in the Franz-Parisi potential and disordered models, but not in the sense that you're doing spin glass, but in the sense that the reference configuration that you're using plays the role of quench disorder. So in fact, in your system, you have emergence of quench disorder, you know, which is not obvious from the beginning, and you can build some kind of effective theory now, you know, at intermediate scales for the local overlap in terms of this quench disorder, which would be some random field and possibly random bonds. Okay, I will not just expand on this. So, remarkable evidence, I think, for remains of the mean field RFOT description in the static properties of finite dimensional models. Of course, question is, the glass transition, this is great, but the glass transition as we know it, it's more about dynamics and relaxation. So what remains in the dynamics? And there it's more, it's less obvious. So let's go to the dynamics. Now, the first thing, as I said, is the dynamical transition, okay, was described by dynamical mean field theory, stuff like this, mode coupling theory, can no longer survive. So it is a crossover in principle. Okay? And the crossover, you know, it's hard to decide whether it's there or not there. So it's been debated for a long time. You know, many years, many decades ago, I argued strongly against it. But nonetheless, despite the fact that I do not like it, it is fair to say, I would say, that there is reasonable evidence for a crossover. Now, a crossover, as you know, it's hard to pinpoint. It's something that crosses over. So it's more or less continuous, smooth, rounded, and this crossover seems to become sharper as dimension increases. This is work by Patrick. So, okay, so there is this, and I will not discuss it anymore. Does it? No, it's just that you have to acknowledge that others have different views and that you cannot impose your view when you're doing an overview, a review talk. I mean, that would be not appropriate. The problem is at the time, people were trying to show that there is a mode coupling transition, okay? And that it was barely rounded and there was a mode coupling transition. And that was clearly, stupid. Now, if you accept that there is no mode coupling transition, unfair. If you accept that there is no mode coupling transition, but you may have a crossover, then it's different, Then it's the mind of the observer to accept that there is a crossover or find that it's too continuous to be a crossover. But then that would explain the change of fair versus unfair. So the main issue is the deeply supercooled liquid, okay, where thermal activation dominates. And again, you have plausible arguments, fits of all sorts of things. But is there evidence for instance, the entropic droplet nucleation scenario? Is there even evidence that the slowdown is controlled or even related to the growth of the point to set length? Okay, so these are basic questions, and actually that are not really, as you'll see, satisfactorily answered. Okay, just to mention that the mapping, then I said, to the effective random field-like model in the statics for the overlaps does not extend to dynamics except near the mode coupling transition, so it's not useful for discussing this. What I like usually to give as an example is the glass-forming plaquette spin model. So I will introduce again another model. I'm sorry for the junior ones. So this is something which has no quench disorder. It's only spins around a plaquette that interact. So they interact around the plaquette. So it's a multi-spin interaction. And you have this with a p spin around a plaquette. And then, for instance, here this is 5 spins around the plaquette. And you will have 5 plaquettes per spins in this particular model, which is the square pyramid plaquette model. And in this model, well, it's been known that this model has something that looks very much like a glass transition, glass-forming liquids, has everything of what is observed, dynamic heterogeneities and all of that, because their dynamics is essentially the dynamics of the kinetically constrained models. That one precisely more something that looks like the East model for those for which it means something. And what happens is that when you look again at what I said was a success of mean field, you look temperature versus the applied external field, well, you find exactly the same behavior as we had for small systems. Okay, so you have a line of first-order transition with a terminal critical point, which is in the universality class of the random field Ising model. And what is different here is that the line comes very, very close to the zero applied field axis, but the TK is really at 0 temperature. So there is still a diverging point-to set correlation length, but it diverges at 0 temperature. But otherwise, everything looks exactly the same as mean field prediction. Actually, what we did with Giulio and others is that you can do the beta lattice version of this, which is a mean field model, but which has also p equals 5 and connectivity 5, and you find this phase diagram here, which goes also to tk equals 0, and which also has also a line of first-order transitions terminating in a critical point. So it looks very much like the mean field RFOT-like behavior that we would predict, and it has those features. But the problem is that in this model, the dynamics is completely different from nucleation argument that predicted by Wallenness. And essentially the reason, which probably is a key element, is that the surface tension between glassy states here is 0. And in fact, the dynamics is like that of kinetically constrained model, and it's described with localized defects where you have not really activation over the length scale of the point-2 set length scale. So despite the fact that you have a growing length scale, the fact that the surface tension goes to 0 means that you have an explanation of the super-Arrhenius behavior, which is different than the nucleation, droplet nucleation argument of Wallenness. And this illustrates, and I will come back to it later, the role of dynamic facilitation, which is present in kinetically constrained model, which they were precisely built around this. And there is recent work actually by Raul Chaco, Giulio Andreoliu, Dave Reichman, on those plaquette models, and that illustrates the role of dynamic nucleation versus dynamic facilitation, versus nucleation to explain the equilibration dynamics of those systems. Okay? So this is one puzzling example. Second thing that I like very much, this is my theory bias, is is the droplet nucleation argument valid? Okay, again, this is something that you can work out in principle, as Peter explained this morning. So these are rare events. So you can describe, most of the time in field theory, you can describe them in a static potential, and you're looking for localized solutions that are, again, you minimize some action, and you get localized solutions. And it turns out that this localized solutions looks like a nucleation droplet that was built, in classical nucleation theory. So the idea of Wallenness was, of course, the same. You look at the Franz-Parisi potential, and basically you would go from here to here through a nucleation droplet. That was the simple argument. Now, there have been fundamental studies on activation on a, simple model, so you're not very far from mean field, okay? You're just slightly beyond mean field, but nonetheless you have nucleation, mean field spherical p-spin model on time scales that are, this is a little bit technical, time scales that are exponentially large on the system size. So you can really look at what is the mechanism for thermal activation in those problems. And it turns out that the scenario is much more complicated than just nucleation of a droplet. I mean, first, the landscape is fibered. Okay, this was this nice picture in Patrick's paper. And second is that those instantons that usually are simple and also occur in a finite time, so it's a finite region in a finite time, in a way, here are anomalous in a sense that they have a diverging time scale. Okay, so this is something very unusual. I mean, they are called instantons because they are supposed to be instantaneous, on a given time scale. And here, of course, if they have a diverging time scale, they are no longer instantons in a way. And then they showed that very likely there's a presence of high energy metastable, what they call hop states, that can connect very different numerous equilibrium states. So I don't want to go into the detail, and unfortunately Patrick will not discuss this tomorrow, but this is something that tells us that at least, the simple nucleation droplets is not the right explanation close to mean field. Now, another point which also I think is important is that, are we sure that the time scale, the alpha relaxation, of course it grows and the point-2 set grow. So you can always make a correlation. Okay? But for the correlation to be meaningful, you should make sure that there is some sort of causal relation between the two. Okay? So lots of people have made lots of correlations, and I think they're just not very interesting, to say um, to stay reasonable. So let me just, I guess I have it, but this is, yeah. So this is 2 experimental data just to show that this is, by Walliness and coworkers, just saying that you can fit all the data, with additional parameters, additional assumptions, additional this. You can go through all the experimental data. And this, I think, it just proves that you're not completely off, but it doesn't show that you're right and your explanation is right. So what we really need is that what? But we know why. It's because the ad hoc assumptions are in the paper, not in the parameters. If you fix a parameter to 1 and you say that it's not an adjustable parameter, you've cheated. One possible, and I think that I will advertise this, and especially now that we have improved simulation algorithms and stuff like this, is that we can look at correlations maybe at a local level. So, with fluctuations. So again, bulk correlation, I have 1 relaxation time, I have 1 length scale, and that's it, and I just change the temperature, are not very convincing. But if I do it, for instance, at Ludovic, I guess it's the only piece of evidence that I know of that you may have some correlation between the growing length scale and the relaxation time, is that you take some kind of mesoscopic system, okay, 111 particles, and in that system, you can both measure the relaxation time, and you can measure the point 2 set length, or the complexity, or all the statistics related to the overlaps. And you can see if there is correlation, and you do it for many samples. Okay, so now the correlation is a sample-dependent correlation. Okay, and here,
Gilles, you have 5 minutes.
okay, I'm close to be done. And here you see that, there is some, not unreasonable correlation between the many samples at different pressures. Here, this here, here, and here. There's 3 different lines. So there seems to be, at least better correlation than what was done before. But to the best of my knowledge, it's the only piece of evidence.
We showed the finite size scaling can be understood using the point set length scale, and that we highlighted as one of the causal.
Yeah. Let's say I'm not completely convinced by this. Is one plausible argument. I agree. So I'm not saying that there are nothing has been done. So this is one plausible argument. It's good that it went that way. But again, usually it's done, remember, what we need to do activation in a deeply supercooled system. And at the time where most of the correlations were done, people were around the mode coupling crossover. Okay? So, and there you shouldn't see all those correlations. It's an argument that I've always had with Sri, is that when he finds that the Adam-Gibbs relation works even, significantly above the mode coupling crossover, what does it mean in terms of real physical interpretation? It's there. There's no question that the correlation is there, but the explanation is not there. Okay? So here I'm saying doing things in a deeply supercool regime that was not accessible before. And that was in the deeply supercool. Yeah, that's right. Yeah, I agree, but I emphasize that it has to be done at low temperature, okay, really. To satisfy some people. No, to check this argument, which is, again, if the 0.2 set is between 1 and 1.2 at the temperature you work on, what are you going to check? But if it changes more because you're at lower temperature, and then maybe some of the other, let me finish, because this is something that I just want to mention. It's dynamic facilitation. So I said everybody agrees, I think, that dynamic facilitation is a mechanism. So it's the mobility in one point facilitates mobility in nearby region, okay, which is different from activation in a local region. So it's really transmitting the mobility. So everybody, I think, now agrees that it plays a key role in the dynamically. You want me to?
1 or 2 minutes.
Yeah, I just have 2 slides. In a spatially heterogeneous character of the dynamics. And this is a priori absent from the random first order transition scenario, but it can be put back in a way, in a phenomenological manner. You could add a little bit of dynamic facilitation to make stuff describe better what happens with dynamical heterogeneities. Peter Wallinus, Sarika, and others have worked on this. But what is at odds with what we know about we think about the RFOT scenario is that from what Camille, Scalier, and Ludovic and others showed is that what we were expecting from the RFOT scenario is that, okay, we have a 0.2 set that grows, especially near the static transition. This is TG here, and this is using this 30 millisecond of the life of a supercooled liquid. So this is super long simulations. And this is the dynamical length scale. So what we would expect is that the dynamical length scale decouples from the static one. We also showed this with Patrick, near the mode coupling transition, but then that they catch, that they go together because everything is related to the activation, to the entropic droplet, to the size of the mosaics. And here it's very different. So the dynamical length scale, if we just rely on this data, then everything can be debated. But the dynamical length scale seems to keep growing at a much faster pace than the 0.2 set length. So this will be my final slide, is that there were recent claims that not only dynamical facilitation, well, there were old claims by Garahan and Chandler, in their theory of kinetically constrained model, but again, it was not fully convincing, to say the least. But now there is claims that the dynamical facilitations not only controls the dynamical heterogeneity, but also the dynamical slowdown, okay, which are 2 different things. One thing is the spatial heterogeneity in your system in the dynamics. The other one is how your time scales slow down with temperature. And they do not necessarily, they are not necessarily related to the same mechanism. As I mentioned, paper by Raul Chaco already that says that it's dynamical facilitation that controls the equilibration time. And then there's this paper by Ludovic and Herrero that says also that the time scale now seems to be controlled by something which is like dynamical facilitation with a dynamical length scale and an exponent that grows with temperature. Okay, so again, I'm putting this. I'm not saying that I'm convinced. I'm not saying that this is the end. This is, these are just a couple of very recent work. Question is, of course, how general, and then the question is, of course, what is the origin of dynamical facilitation? And then there's another line of research, related maybe to elasticity and to something that Jeppe has worked on. Okay, so this is the end. So again, striking signatures of this mean field RFOT scenario in the static quantities, for sure, and this is impressive. In sharp contrast, I must say that there's a very meager evidence for the RFOT mean field extended to RFOT scenario in the dynamics so far. And this is, what I would think would be nice to do with, again, improved algorithms to try to go beyond is what the present status. Okay, and here I guess I have to stop. Thank you.
Thank you. Yeah. So we'll have maybe 1 or 2 quick questions. And
sorry.
You mentioned instantons, and it's already. Can you just you mentioned instantons? Can you comment on how we can picture these instantons and the role they have in?
Okay. Well, as I said, you take the ferromagnetic case. Okay? So you have a double well potential with a metastable minimum and a stable minimum. And you're asking yourself how I go from the metastable to
okay,
the
so
stable.
you're just talking about the
barrier
states.
crossing.
Okay.
And this can be done in the static potential or in the dynamic, which is important here for glasses.
So about this connection with dynamic facilitation, I want to sort of step back and just sort of look at simple nucleation phenomena, right? If you look at standard nucleation theories, they're actually, in some sense, very simple-minded in assuming that the neighborhood of a nucleus always remains the same as the metastable state, that's your parent phase, right? Which in reality should not be valid for even the simplest of nucleating systems. Somehow there are assumptions about the time scale for which you achieve that metastable equilibrium condition in the presence of the growth of a nucleus. So I think, instead of, there are different ways of stating what you said. Instead of saying a nucleation-like picture may not be a good description, I could also take a lesson from this to say, in fact, nucleation can be more complicated than how we normally think about it. Is that sort of helpful?
I think I'm saying there's two different things. I mean, I think for nucleation in general, for crystal liquids, all of that, even ferromagnets, I mean, it's more complicated than just the droplet classical nucleation over in the instanton in the 5-4 theory. Okay, so it's more complicated, yes. But basically, the nucleation argument with the droplets gives you, a zeroth order description of what's going on. And this is the kind of mechanism that is used by the system. Now here, there's no evidence at all that this is the kind of mechanism that is used by the system. And this is what would be, again, needed and interesting is if, that's what I said here, if the work done by Tommaso Rizzo, Patrick, Giulio, the others, Valentina, could be extended to see what it looks like. Is it, if there's no nucleation droplet, so what's the shape of what's going on? And a hub state with an exponentially large number of metastable states to go from one equilibrium to another, it's not my vision or my picture of a nucleation droplet. It is, which is what they found in those systems. So there is a need to try to build also, maybe it's not worth it, maybe it's too complicated, I don't know. But there is a need to build a picture of how relaxation, activation proceeds in those systems. And we're barely at the start, I would say.
Sarika.
I had two questions. I'll just, they're short. I think your answers will be like, they're basic questions. One is you said some level of coarse grading to define the ZPTS, which was written on your slide. Yeah. So I would like to understand that. And also I was wondering, cannot be a combination of nucleation and facilitation, like, it's a complex structure. So can't the whole dynamics be a combination of these two?
Okay, so on the first one, what I said is that point to set lengths cannot be defined just at the particle level. Right. So you need something. You need a group of particles of the size of point to set lengths to define it, and it's the same for overlaps. It makes sense at a coarse grain level, not just particle per particle level.
So you mean the PTS should be recalculated now?
Should be
recalculated with some kind of coarse graining concept?
I think just taking, when I said, because I had said local quantities. But in fact, local quantity is not particle-based. That's all what I meant.
Right.
Local quantity means that you need a volume that is, in the case of Ludovic's, it's 111. Maybe you don't need 111. The best would be to do it in a cavity, because there, in a cavity, a priori, you suppress dynamical facilitation. So this is where you can directly test that your dynamics inside the cavity, if you could equilibrate, just scales with the 0.2 set that you have measured, the size of the cavity. Now, for the second question is that I think that before we mingle activation, which I think would be necessary, activation and dynamic facilitation, we have first to understand what's the description of the activation. And my point is that I don't think right now we know what it is. And I don't think it's clearly not a droplet, entropic droplet thing. But of course, the fact that we should mix, some kind of possibly, if we show that it's there, activation on the 0.2 set length, dynamic facilitation, plus some local order fluctuation, of course, that would be the theory of the glass transition. We just want to make sure that all the pieces first are there. So that's why I think that, as I said, working in a frozen cavity and looking at correlations there would be important.
Okay, if there is no more question, then I think we should thank Gilles for this enlightening talk. And it's unfair to keep Gilles away from coffee for so long after.
Oh, yeah, no, it's unfair, it's unfair.
Okay, I think
Thank you for bringing the fairness again.
Then we go to coffee, and also there's a poster session along with it. High tea and poster, okay. High tea, high coffee, and poster.